So we're talking about section 7, the rigorous definition of the limit. The rigorous definition of the limit. The first thing we did was talk about this cannot be the same marker that I put in. Okay, this is the first thing we did last time was just talk about sequence notation, right? Sequence notation, that's easy. Okay, right. We write sequences, to recall, right? I have something like this. This denotes the sequence A1, A2, A3, etc. Okay. Okay, so we want to talk about this thing called the limit, right? And so we ask you, what do we mean? What do we mean by limit? You've all seen the notion of limit before. What does limit mean to you? What's a limit of sequence think?
As n approaches infinity, where doesn't have to reach that value, but what value does it approach?
Okay, so what value does a sub n approach as n goes to infinity? So it's sort of the answer to the question. What value does n approach? Does a sub n approach as n approaches infinity? Okay. Yeah, that's basically right. So you have so for example, if a sub n is 1 over n, right? As n goes to infinity, right? So as n goes to infinity, then this a sub n goes to 0. A sub n goes to 0. If I have this other example, suppose a sub n is -1 to the n. Right? As n goes to infinity, then what happens? Do we approach anything? The answer is no, right? It bounces back and forth. Right? So no. Right? So examples and non-examples. Let me give another example. Suppose we have something like this. A sub n is 1 over n whenever n is not a power of 10. Okay. But it's 1 if n is power of 10. So what does this look like? Well, A1 is 1, A2 is a half, A3 is a third. It looks like the first sequence, but when you reach 10, A10, you get a 1. Okay. A11 is 1/11th, A12, A12 is 1/12th, etc., etc. Things go fine until you reach A100, at which point you get a 1 again. Okay. Right. So it looks exactly like this thing, but at A10, A100, A1000, A10,000, etc., etc. Farther and farther apart, but consistently, you keep on coming back to 1. Okay. Does that have a limit?
No.
No. So we don't consider that thing to have a limit, right? So even though on the whole things are tending towards 0, periodically we jump away, right? Even if it's getting farther and farther between, right? So at 1 million, at 10 million, right? At 10 million, etc., etc. Okay, so the notion of limit has to contain some idea of inexorability, right? It's inexorably tending towards that number, right? I mean, it may waver, but you have to be able to say that it gets. You can make the control finer and finer, right? Right? You have to say like these guys. You have to be able to say that if I want these guys to be this close, then I can find some time. I can find some time past which everybody's that close, right? I have to be able to find that time. Here I can't do it, right? It's like I'd like to make everybody this close, like within a half of 0. You know, I'd want to be. If the limit is 0, I should be able to make the limit to make these guys all the elements within a half of 0. But I can't find any time where that happens, right? I can't find any time past which that happens, right? Like even if I'm way out here, I think okay, I'm safe. I'm in the billions. But when I reach 10 billion, boop, I jump more than half away, right? I can't do it, right? So you have to be able to answer this question, and this turns out to be the key component of the notion of limit. Yeah, Marco.
But the bounce would be okay if the instead of 1 you had some function that was also getting smaller.
So yes. Yeah. So for example, suppose this thing is going to be like 10 over n, or a billion over n, some huge number over n. I don't know what it is. A trillion over n. No, it's a billion. Right? Billion over n. Okay. So you have a billion over n. That's actually okay, right? Because if I say I want everybody to be less than a half, I want everybody to stay within a half of 0. Well, can you find me a time past which that happens? Can you find an n past which all the a sub n's are within a half of 0? If it's this guy, so it's the normal 1 over n guy, but at every power of 10, you jump up to a billion over n.
So any value greater than a billion?
Any value greater than...
Because the next time it jumps will be 10 billion.
Yeah, that's true. So anything, as long as you're past a billion, you're good. Do you see that? Right? The answer is yes. Take n to be 1 billion. Right? Because at the next jump, you're going to be at 10 billion. The value is going to be 1/10. Right? At the next jump after that, you'll be at 100 billion. The value is going to be 1/100th. So if it's jumping like this, but the jump is decreasing, then you're okay. Okay. So yeah. So I hope you're starting to see what the limit means. Right? The limit really means that you can control. Like I can make all the elements as close to the value as I want. Okay. If somebody says I want it to be this close, there's some time past which that happens. Okay. This is really the definition. Okay. So here's the formal definition in mathematical language. If for every epsilon there exists an n past which a n minus l is less than epsilon, then can we say a sub n converges to M? In other words, the limit of a sub n is L as n goes to infinity. Okay, so there's different notations, these are all valid, right? People write the limit of a sub n as n goes to infinity is L, or that a sub n goes to L. And sometimes people, to make it clear, write n goes to infinity on top of that. Not necessary. Typically, you know that n is going to go to infinity. A sub n goes to L. Okay, so let me just give a simple example. Maybe this example was a little bit not the first example I should have given. So here's the example. This sequence converges to 0. Right? That's intuitively, you believe that, even if you don't know this definition over here. Now let's see how this works with the definition. So I'll ask a bunch of questions. For what n is it true that past that point we're guaranteed that a sub n minus 0 is less than 0.1? Don't blurt it out. I'm sure you know the answer. Look at it for 10 seconds. For what n is it true that past that n, we know that a sub n minus 0 is less than 0.1? Okay, turn to somebody nearby and say, it's this. Capital N is going to be 10. Capital N is 10, right? And because you know that, you know that past 10, right, at 10, your value is 1/10, right? And if you're past 10, then your value is it's smaller than 1/10, so it's distance from 0. Remember, this is a distance, right? Distance of a sub n to the limit is smaller than 0.1. As long as we're past this point, everybody is within 0.1 of 0. If I say ensures that this thing is less than 0.01, well then what's your n? 100. What? 100, right? So with an epsilon being 0.1, then n turned out to be 10. With an epsilon being 0.01, then n turned out to be 100. And if I make my epsilon to be 0.001, then n is what? 1,000. Okay. And if I make my epsilon equal to epsilon, then what's my n? Epsilon is some number. Epsilon. Epsilon is. So don't answer. Don't blurt it out. Write down an answer. Right? If I say the epsilon is epsilon, what's the n? Okay, turn to somebody nearby. Tell them the answer. Tell them what you're thinking.
It's epsilon is 0 and n is infinity.
No. Epsilon is some number. Epsilon is some positive number, right? Epsilon is some positive number. answer?
1 over epsilon.
1 over
1
epsilon.
over epsilon. 1 over epsilon, right? Right, so, you can, so there's a pattern, right? If my epsilon is 1 billionth, then my n is 1 billion, right? When my epsilon was 100th, my n was 100. When my epsilon was 1,000th, my n was 1,000, right? Epsilon is epsilon, my n is going to be 1 over epsilon. Why does that work? Well, if n is bigger than 1 over epsilon, right? So if n is bigger than 1 over epsilon, then you know that 1 over n is less than 1 over epsilon. Right? You can prove it algebraically. Right? If little n is bigger than 1 over epsilon, if you're past the 1 over epsilon point, that means that a sub n, right? That means that a sub n, which is 1 over n, is less than 1 over epsilon. I'm sorry, is less than epsilon. That's why you guys were like. Okay, yeah. A sub n is going to be less than epsilon. Right? So as long as, if somebody says, I want you to stay within this tiny, I want you to stay this close to 0, you say, oh look, as long as I'm past 1 over epsilon, then all my values are less than epsilon. Okay. Right. And so you see that we satisfy the definition of the limit, right? Right? We're trying to show over here that the limit of 1 over n is 0. So we want to show that the limit, as n goes to infinity, the limit of 1 over n is 0. What do we need to do to show that? We need to show that given any tolerance, given any tiny epsilon, there's a point past which all your values are within epsilon of 0. And we've done that, right? We've said, look, right? We said, look, so let me write it out formally. So look, in other words, we want to show that given any epsilon, there is an n such that if we're past that n, then the distance of a sub n to 0 is less than epsilon. Okay. So you say, well, given our epsilon, take n to be 1 over epsilon. If little n exceeds that, we see that the distance between a sub n and 0, that's the same thing as the distance between 1 over n and 0. Right? A sub n is 1 over n. Right? But that's the same thing as just 1 over n, right? Because this is a positive number. Right? 1 over n is less than epsilon. Right, since n is bigger than 1 over epsilon. Okay, so what we see is that given any tolerance, we can find a time past which that tolerance is satisfied. Given any tolerance, like I want you guys to stay within this amount of the limit, we can find a time past which everybody, the distance of any point in your sequence, is within that tolerance of the limit. Okay, and that's the end. Okay, so that's how you, this is a most simple example of a proof of a limit. What do you have to do? You have to show that, to show that a limit is valid, you have to say, I can play the epsilon endgame successfully. Okay, right? You say, no matter what epsilon I'm given, I've got an end that answers it. The epsilon is the enemy, the n is your answer. Okay. So no matter what epsilon you give me, I've got it. I've got something for it. Okay. I can play the epsilon endgame successfully. I show that I can do it. That means that the limit is valid. Okay. So this is what the limit means. Okay. That you can play the epsilon endgame successfully. It's not what you might have thought. That you can make, you can make your elements as close to the limit as desired, given control over how far out you take your elements. Okay, let's stop here. Let me think. Yeah, okay. We don't have time to go on. Let's stop here for now. Let me just say one thing, which is that, it has to be for any epsilon, right? The fact that you could play the epsilon endgame for some fixed epsilon is not enough, right? If you say, oh look, I can make everybody within 1 of 0, that's not enough, right? It has to be like, you have to be, no matter what epsilon you're given, right? No matter what epsilon you're given, you can find a time past which everybody is within that epsilon. So no matter how small a tolerance you're given. Okay, that's it.